Okay. Good afternoon, everybody. Ready? Okay, so we are in the last class. I gave some assignments. How many of you got a chance to go through it? Yeah. What did you do? Okay. So the two problems were, number one, a metronome generator, and the other problem was real-time pitch estimation. So today I'll give you some demo of what I meant by that. Okay, let me turn my screen. This is a complicated thing, don't worry about it. I will just tell you the metronome part. So let's see if you can hear this. You can hear it, right? Like it's just playing. Maybe you take a stick and right now I can see I increase its beats per minute or BPM. Basically the frequency. Right, I'm clicking this plus button. I'm clicking this plus button, and it's increasing on the fly, without stopping, without breaking the rhythm. It is just increasing. Likewise, I can decrease it also. So 100 BPM. BPM means beats per minute. This like you have frequencies per seconds. This is per minute because number of beats per second will be like 1, 1.5. So to avoid decimal numbers, we just multiply it with 60 and round it off. So some integer beats per minute. Okay, that's the frequency. Now, this is called a metronome. It just gives you tick-tick sound. What is the utility? Utility is in music, when you are singing, you want to keep track of the timing. Let's say I am, okay, you remember last time we discussed one problem. Let's say if I am singing and Sanreet was that time, but maybe, what's your name at the on the last bench? Aditya. Okay, so Akshat or Aditya, anyone. So let's say Aditya is playing some drums or something. There will be so much of delay between the two, right? So what people generally do, like not in India, but at least I have seen it in the Western music, what people do is that they take a device, synchronize it. Let's say you take metronomes, two metronomes, synchronize them, and then you go with your metronome, I'm going with my metronome, and then you follow your metronome, I'll follow my metronome. Means, let's say you're playing drums, don't try to synchronize with me, try to synchronize with the metronome. Likewise, I will also not try to synchronize with your drums because there will be a delay. I'll synchronize with my metronome, right? So that's what metronome is used for. And also it basically gives you an idea of timing so that you can synchronize. That's the major use of metronome. Any questions so far? No? Okay, now somebody may ask, why to just confine ourselves to tick-tick sounds? Can I not make drums only, like entire drum system with this metronome or with this setup? So that's what we see here. this audio has got 4 beats in one cycle, right? One cycle is, you're seeing the numbers here, right? 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, right? So it has got 100 beats per minute, and each cycle has got 4 beats. Tell me what is the periodicity of this signal, the time period of this signal, or whatever, frequency of this signal. Quick. 2.4 seconds is what? 2.4 seconds is the time period, huh? Okay. Any other answers?
In one cycle of 4 beats, they are different or they are same?
Different beats. You just heard them, right? Why are you asking when you heard it? I will just play it again for you. Tell me the periodicity of this signal, means the time period or frequency, whatever. Yes? 2.4 seconds is the time period you are saying. Okay. Any other answers? No other answers? Okay, let's compute. I don't know the right answer. Let's compute it. So you have got 100 beats in 1 minute, means 60 seconds. So the question is 4 beats. So 4 beats will be in how many seconds? So you do 60 upon 100 into 4, 240 upon 100, so 2.4 seconds. Yeah, so 2.4 seconds is the right answer. So means that periodicity, the time period of the signal is 2.4 seconds. Okay. Yeah. Now, the question is, can you write a program to simulate this metronome? In an instrument, let's say you have tabla or drums, you have some strokes. Each stroke sounds differently. Let's say one stroke could be, like if you have a tabla head, you can strike. We don't have Parampreet here. Did you call Parampreet? Oh, he's coming. Okay. So Parampreet knows tabla. So here is it. So Parampreet knows tabla. Correct me if my understanding is wrong. So when you play tabla, you have different strokes. Like thin, where you have, let's say, I need something circular. So like let's say this is a tabla head. You play like this is some different stroke. You play like this is a different stroke. And you can make different strokes. Now using different combinations of these strokes, you can create so many talas. So tal means basically this thing. You have, first you tell me how many beats are there in the cycle, tal cycle, and then what are those beats. Right? That is one tala cycle. Boom. Simple concept. Just the strokes are there. You put strokes in that structure. That let's say there are 4 beats. Then first beat will have tin tin, then dha dha, then tin dha, something. Then it becomes like one beat cycle or tal cycle. So the question is, if I give you the strokes and I ask you, can you generate this infinite loop for me? Somebody can say, okay, I will create an audio of length 1 hour and I will save it. But I say, why to waste so much of memory when you can generate it on the fly? It's just a circular loop, right? So that's the point. So the problem which was given in the assignment was a simpler problem. You have only single stroke. Let's say clap or just a tin something, single stroke, and you have to make an infinite loop generator. I will specify that BPM also. So the input is BPM and the single audio file, that's short stroke audio, and then you have to generate the entire infinite loop metronome, right? That's the problem. Right. So you understood the problem and you understood the relevance, that how this system can be used to create this software like this. Right. This was the first problem. So what I want you to do is, in the next Monday class, bring a write-up, submit it. In this write-up, you will be telling me your design, how you are going to design your metronome or this thing, right? Where input is audio file and the BPM, output is the infinite audio generator, infinite loop audio generator, and the BPM should be varied dynamically. Means I may, just like here you can see, I play plus, I press the plus button, it increases dynamically. I don't have to stop it, again play it, right? It's not static, rather it's dynamic. So I want a dynamic metronome with a single stroke where BPM can be varied with a slider. And for Monday, you just need to present a write-up. You just bring a write-up and that's it. You don't have to code it. Just bring the write-up with your strategy. How would you implement such a system? Using the concepts which we have studied before. All the DSP concepts you have studied. So that will test you or kind of evaluate how well you have understood the DSP things. All right? Okay. Second problem was this. Second problem is this. So see this, it's written here C. I'll play the, okay, first of all, just see here. So whatever I speak, my pitch will be displayed here. C. This is F, and the frequency is also mentioned here. Frequency is what? This is the fundamental frequency, right? You have seen the audio waveforms. They were not sinusoidal, but they were periodic. So they will have one fundamental frequency and remaining all are overtones or harmonics. But we are interested in the fundamental frequency. So the fundamental frequency is displayed here. Right, Parampreet? Okay. Because he is a regular user of this app. I don't use it very frequently. Okay. E or this 164 something. This is what you have to make. In real time, it should capture the audio and display what frequency is there. Right? Easy? You have studied pitch estimation methods, right? Autocorrelation and DFT based pitch estimation. You have seen all those plots. Did you go through that pudding.com page I shared? The link was not, but the link is available on our website, no? On. Okay. Okay, I'll share it again. Okay. So these are the two things which are. So you have to prepare a write-up for both these problems, and the maximum limit is 1 page for each problem, like 2 pages total, 1 page per problem. And then minimum font size is 9 or 10. 10 I think is fine. And you can add images. So make it very impressive. Make your solution very impressive that I just see it and I understand it. And then we will evaluate who gives the best solution. Right? By the way, this app costs how much, Parampreet? Huh?
2,800.
About 3,000 rupees per subscription. So if you can make it, then you can earn money. Yeah. But the point is that this has a great utility in music. Everybody uses it. Means Western music, Indian music, everybody uses metronomes or frequency tuners. How many of you play some instrument? What do you play?
Flute.
Flute. So in flute, I think you don't need to tune the flute. Do you need to tune? How do you tune it? With tanpura?
To match the airflow. We can't tune the instrument, we tune the airflow.
Oh.
Change the seasonally.
Okay. See, so many nice things I'm learning. What else do you play? Oh, you can also use a tuner like this.
Yes, sir, I use.
You use the iTabla Pro.
Not Pro, free version.
Free version, okay. So, but you use that feature?
Yes, sir.
Okay, good. What do you play? Somebody else raised hand. Harmonium and tanpura. Harmonium does not need any tuning, right? Harmonium is pre-tuned. What else? Who else plays something?
Piano and drums.
Piano and drums. Piano also is pre-tuned.
I mean, you said to be tuned, right? The
Huh?
grand piano has to be tuned regularly.
Pardon?
The grand piano has to be tuned regularly once in 6 months.
Ah. Grand piano means an acoustic one. The acoustic one.
Drums need to be tuned.
Okay. Yeah, it's an acoustic thing. Yeah. So, but I hope you don't have a grand piano in your room.
No, electronic one.
Huh?
Electronic one.
Electronic does not have to be tuned, right?
That doesn't.
Okay. Yeah. And tanpura is an instrument. It has long strings, so those have to be tuned. It's a string instrument, so strings can become loose or tight. So you can tune it using this kind of a tuner. But some people, they just tune it by ear. Those who are more expert. Okay. And this is also very useful for learning music. Let's say you want to see whether what I'm singing, my pitch is matching the tanpura or not. You can use this. Okay, fine. Any questions? Otherwise, we'll move to our next topic. Okay, so today, in the last class I asked one question. Harmonics are missing. Why the harmonics are missing? Did you do it? Could you find an answer? No. Yes? No? Should I do it or I leave it to you as an exercise? Leave it, okay. Okay, next class we will discuss. Spend some more time. Remind me in the beginning of the next class, I will discuss the answer if you are not able to find. All right. Okay, I need to just, one more concept I need to discuss regarding the metronome. So in metronome, when you have some sound, it generally looks like this. You can see my screen, okay. So this is time axis. So when you hit let's say the stick, when it hits the table, it makes a sound. So this sound looks like this. Right? This is sharp, peak, and then when you will make a metronome, what will you align? Okay, so maybe I'll just tell. So this point, so out of these points, which of the points is known very sharp, very precisely? The first peak. But what if I hit it harder? The first peak may move, right? This start point is known most precisely because it's causally related with your strike. As soon as the stick will strike the table, immediately the waveform will rise. And this rising, the point where it starts rising, that is known most precisely. It's causally connected with the person who is hitting it, right? So therefore, this is most precisely known time. This is a hint for you when you design your metronome, then you can use this information. Let's say you have multiple kind of strokes. One stroke is this, one stroke is this. So how will you make the periodic sequence so that let's say this is thin, this is dha. Thin dha, they are equally spaced, means they occur in proper time. So if you try to align their peaks, it will have some error, although very small error, but still some error. But if you align their onset times, or this first point, then it will be more precise. This time is called the onset time. So this is time. This is called the onset time. Now you will see this onset, the whole thing increases. So this area is called, this area is called attack. And then approximately this area is called the transient. A signal is kind of, it's just called transient. And then this region where it is decaying, it's called the decay. This is a common terminology used in literature. You have an onset time which is very precisely known. Then you have an attack where basically it is gaining intensity. And then there is some region where the volume is very high, it is kind of very distinctly audible. That is the transient region. And then it slowly decays down. That's the decay. So when you are designing your metronome, you can align the onset times. Okay. And now I will start with today's topic. So today's topic is very simple. So we have, in the previous weeks, we saw digital signal processing or discrete signal processing, and then we saw different aspects of DSP, for example, systems, discrete time systems, and then we saw different ways to analyze their periodicity. Then we came to discrete Fourier transforms, then we discussed convolutions, etc., etc. So today we are going to start the new topic, which is, we also discussed basics of audio signals, right? We discussed about Pratt, we discussed about properties of audio like pitch, intensity, etc. So today we are going to discuss machine learning basics. How many of you have done machine learning before? How many of you have never done machine learning before? 1, 2, 3, 4. Okay. If you have never done machine learning before, these basics will help you understand the bigger picture, but then I would recommend you to watch the MLSP videos which are available on YouTube. Maybe 5-6 videos are there. You can watch them and you can get the detailed picture. And rest you learn as you go. Means once you start working on some problems, you will understand better those concepts, and then you can go into further details. But I would recommend that if you have not done machine learning before, please go through MLSP on YouTube, MLSP course on YouTube. Okay, so before we start machine learning basics, let's understand why we are doing machine learning. I divide the whole thing into two paradigms or two parts. One is called the world, where things are happening. You have a musician sitting who is playing music. You have a person sitting who is speaking some language. You have everything is happening. Now you want to make a machine. The other part of the world is the machine, which wants to emulate certain things. For example, Alexa is emulating how people understand speech, or people transcribe speech to text in the world. Or some forecasting system is trying to predict the weather after a week or after a few days, trying to emulate the actual world, which will generate that temperature after 2 days or a week, right? So we have the world and the machine. Now the world knows things. Assume the world has all information, and the machine does not have all the information, and the world will give some information to the machine, not all information, but some information, using which the machine has to train itself to be able to predict other things. I'll give an example here. Let's say a very simple task is, if I show you a flower and I ask you which flower is this, you can tell it's a rose or a lotus or a jasmine, right? Now, can a machine also tell this? So here world has two things. One is the X and Y. X is, let's say, a data point, maybe the height of the flower, diameter of the flower, etc. Y is the label of the flower. Let's say I say, this is my flower, it's a rose. And this is also a flower, this is also a rose, this is also a flower, this is a rose, this is a flower, this is a rose. This is a flower, it's a lotus. This is a flower, it's a lotus. So these are lotuses. And then maybe some other symbol, like maybe these ones, they are jasmines. Right? So the world knows it. Now, okay, when you are doing machine learning, you have to simulate both the worlds, both the paradigms. You have to simulate the world, you have to simulate the machine also. So the world will give the data to the machine. Okay, take it, these are all roses. Take it, these are all lotuses. Take it, these are all jasmines. Machine got all that data. This is called the training data, right? And then, after some time, machine will give it a kind of an image, but machine will not tell whether it's a rose or a jasmine or a lotus, right? So the machine will give it only this much. Although the machine knows it's a rose, but machine will not tell it to the, the world knows it's a rose, but the world will not tell it to the machine, right? And the machine has to guess what it is. Let's say the machine got trained here in this stage. It's called the training. And then this is the test time. Now the machine gave an unknown symbol. Now the world gave an unknown data point, which means it told the height and diameter of the flower, but did not tell what is the label of the flower, and machine has to tell what is the label. So machine will guess, maybe it's a lotus, and it will return it back to the world. The world will compare the two things. It will say, wrong, you are wrong. I will deduct your points. Your accuracy is 0%, or your points are 0. And then the machine will give it another test. Okay, tell me what is this. And machine knows it's a jasmine. The world knows it's a jasmine. Machine has to guess. Machine says, okay, maybe it's a jasmine. It returns back to the world. World will say, right answer, it is a jasmine. I'll give you full points. And then you can take the average points, and then you will say, oh, this machine got this much performance. Maybe some other machine, maybe Sumit made one machine. What's your name? Vineet made another machine, and I am the world. So they gave me their predictions, and I will compare with my ground truth, which I know. And I say, okay, Sumit got this much points, Vineet got this much points, and then you can decide whose machine you want to work with. That is the idea of supervised machine learning. Right? Any questions here? Okay. Now, to understand it graphically or geometrically, you can plot the height is here, the diameter is here. Let's say you got a rose. Rose has got more diameter than height. Rose, another rose, another rose. And lotus is, maybe it's a closed lotus, more height than diameter. Lotus. So closed lotus. So more height than the diameter, and these are the lotuses. Now, how will you make a machine model, a mathematical model, which will tell you whether it's a rose or a jasmine or a lotus? So, there are many common ways. One common way is, let's say, okay, now that the unknown thing comes in, the unknown thing lies somewhere here. What will you mark it as, a rose or a lotus? Lotus. Why? Yeah. How will you make a machine tell? Machine knows only this much. No, machine knows all this information. Machine does not know the label for this. The machine has to tell you the label for this. How will the machine tell?
Compare height and distance.
With
Diameter.
with what?
Between each other, like if the diameter is greater than height, that it's
Okay, means okay. Yeah, fine. Agreed. For this case.
The unknown image is closer to the stars.
Good, good. So unknown image is closer to the stars, so it must be a star, right? So these are two different approaches. I will start with Sanjeev's approach. You have fallen somewhere. Just ask your neighbors, who am I? Neighbors will tell you, oh, you know, I am a jasmine. I am a jasmine. I am a lotus. I am a lotus. I am a lotus. So all the neighbors are saying I am a lotus. So I must also be a lotus. Right. So I will say, okay, I'm also a lotus. So the machine will basically compare the nearest neighbors. Machine got a point in 2D space. It will find out of all these 8 known points, which ones are the closest. Maybe top 2, maybe top 3, maybe top 4, whatever. So let's ask top 4 people. And the top 4 people, all of them, they say, I am a jasmine. Oh, I am a lotus. Machine will say, okay, this must be a lotus. So machine returns the answer. It's a lotus. Most likely that is correct, but the world can tell. Likewise, if the unknown point falls here, then the machine will say it's a rose, looking at the neighbors. But what is the problem with this approach? The problem is finding nearest neighbors from a list is computationally very expensive. If I give you a list of points, let's say I give you a list of 1 million points, which are like 2-dimensional or even higher dimensional. Then I give you 1 point and I ask you, can you tell me which is the nearest neighbor, or what are the top 10 nearest neighbors? How will you do it? The complexity will be of the order n. Like there are 1 million points and the complexity is almost 1 million of that order. It's very costly, very costly. So with the large data, for the big data, it is not a good approach. So the other approach is what you suggested, right? You suggested the other approach, right? Oh, so Vinit suggested the other approach. The other approach is, can we create a boundary? Let's say create a line segment here. And this line segment is placed in such a way that it separates the two classes. What is the equation of a line? So D equal to mh plus c. Here m and c are placed in such a way that the line is it separates the two classes, right? Now the question is, let's say you know the value of m and c also. Now I give you the unknown point, this unknown point. What is on this line? Let's say let's make it like this. D minus D plus mh plus c is equal to 0. Let's call this as a function of D comma h. Right? This is a function of the data. D and h is basically x. Right? X is D comma h. X is a vector which has height and diameter. Now fx is this. Now on the line fx is 0. If I go to the rose region, what is fx? Greater than 0 or less than 0? means you know the line. This line is there. Okay, m is, let's, tell me typical value of m. Huh? How, let's say roughly 1 or a little more than 1, 10 something maybe. So m could be roughly 10. And c is how much? Something negative, maybe -5 or something. Let's take it as -5. Okay, now tell me fx. Your point was good that if I take m as -10, c as +5, no, since it is -d, no, that point is not valid. Okay, tell me now, what is fx? What is fx in the rows region? Fx will be positive or negative? Positive. How many of you say positive? Raise your hands. 1 person is saying, 2%, 3, 4, 5 are saying positive. Negative? Raise your hand. Don't be shy. Raise your hand. Negative. Why do you think it's negative? Huh? Okay. Yeah, that's a good way to guess. Yes, the origin is on that side, so it should be negative. Because on 0, 0 it is c only, so which is -5, so it's negative. Okay. Another way to see it is, you stand here, you are on 0, f is equal to 0. You go in the positive d direction. Since it is negative, so it will become, whole thing will become negative. Right? Everything is constant, just your d has increased by some amount. So by that much amount, f will decrease. So therefore, this is the negative region, and this is the positive region. Likewise, if you here you increase h, since h is positive, so basically the what do you say, the derivative of f with respect to h is positive, so it will increase. Okay, that's it. So.
The point in value, I said the sign of c. The sign of c, it depends on sign of c.
Yeah, but if you take c as +5, then this line will be something, it will change. Right? Your c line will move here. So because the coefficient of d is fixed, that's why the whole thing sign becomes fixed. If I would have said here m1, m2, and c, then certainly you can choose the sign. So it had that degree of freedom, but right now it doesn't have that degree of freedom. Okay, so this is called a linear model. It's called a linear model because why it is called linear? Because f is linearly dependent on the parameters. What are the unknown parameters here, or the trainable parameters here? M and c, and f is linearly related, which means df upon dm is independent of m, and derivative of f with respect to c is also independent of c. So which means they have a linear relationship or an affine relationship. Okay, so linear models are fx is equal to, in general, w1, okay. Something, right? So for example, in this, if x is 2-dimensional, then this is w1 x1 plus w2 x2 plus w0. Right? That's the equation of a line. If you write it in terms of vector notation, then it is w transpose x plus w, right? And fx is positive or negative. Depending on that, you can decide your class. This is a linear model of classification, let's say. Now let's have a word about how to evaluate your model. Let's say I want to compare the model of Sumit and Vineet. Which one is better? So what matrix can I use? Let's say it's a binary classification. Let's say whether I want to detect whether it is a rose or not a rose. Rose or not a rose, binary. So what will I do? First thing is confusion matrix. This gives me a descriptive overview of what is happening or how the model is performing. Confusion matrix is, so this is the ground truth or the actual. Let's say it is either yes, it is a rose, or no, it is not a rose. And then this is the predicted. Right? If I'm the world, let's say Vineet is the machine, or Vineet has a machine. If I give a rose to Vineet's machine, and Vineet's machine says it's a rose, where will I put the entry? First cell, right? 1, 1. So it is called a true positive because Vineet said it's a positive, that yes, it's a rose, positive. And actually it was true because it was actually a positive. So it's a true positive. So true positive. Let's say I gave him a lotus, but Vineet said yes, it is a rose. Where will I put the entry? Huh? Here?
Yes.
Or here? How many of you say here? How many of you say here? And how many of you say nowhere? The others who are not raising their hands. So it is here because, actually it was a lotus, so means it is somewhere in this row. And Vineet's model said it is a rose, so he predicted here. So it will fall here. So which means the Vineet's model said it's a positive, means it's a rose, positive, but it was not positive actually. So it's a false positive. So false positive. Now you have, let's say I gave him a rose, but he said no, it's not a rose. Where will it fall? Here. So I said it's actually a rose, but Vineet's model said not a rose. So that's why it's called a. So Vineet's model said it's a negative. I mean, it's not a rose, it's a negative, but it was wrong. So that's a false negative. Now I gave him a lotus and he said it's not rose. That will fall here. It's called a true negative. So his model said it's a negative, and yeah, it is negative, so true negative. Right? This is called a confusion matrix. This we did for a binary classification, but you can do it for multi-class classification also. Let's say rose versus lotus versus jasmine. You can create a three-dimensional thing where this is ground truth, this is predicted, and this is rose, lotus, jasmine, rose, lotus, jasmine. So you can see a detailed picture that my model is confusing between these two classes. Maybe the jasmines and roses, they look very similar. That's why their sizes are quite similar. So my model is making a mistake. Whereas lotus is large and its size is different. So my model is not making so many mistakes. So all these detailed analysis you can do using confusion matrix. But the problem is that it does not give you a single value based on which you can compare which is a better model. If I ask you which is a better model, Vineet's model or Sumit's model, you may say, yeah, Vineet's model gives you a good true positive, but false negative is lower than Sumit, and so or true negative is lower than Sumit. So then you will be confused. So don't give me so many parameters. Give me just one value based on which I can just order them, which is better than which. So that one metric will be, any guess? Accuracy. So what is accuracy? The formula for accuracy will be true positive plus true negative upon everything. Right? So the correct ones, when the diagonal divided by the whole, the entire sum of all the entries. Right? The trace divided by sum of entire matrix. Trace upon sum, basically. But accuracy may not be a good metric if you have very less positive samples anyways. Right? So let's say if I make a machine to detect COVID, and in the class only one person had COVID, right? So I made a machine which will try to detect very nicely. So it detected one person who had COVID, but it also, for 2-3 people, it also kind of said they also have COVID. So what is the accuracy? Let's say there are 50 people in the class. Okay, problem statement. 50 people in the class. One has COVID actually. Machine predicted, yes, this person plus five more people it predicted, they have COVID. Right? So what is the confusion matrix? Draw the confusion matrix. So something like this. This is the ground truth. Positive, negative means basically COVID is there or COVID is not there, or 1, 0, whatever. Yeah, fill up the entries of this table. Yes? 10545, huh? 44, okay. So there was one person who had COVID and the machine also said it has COVID, so 1 here. Then there are 5 people who did not have COVID. They were negative, but the machine said they are there, so it's like a false positive. So how many? 5 people. And then rest all machine said they don't have, and they also didn't have actually. So 44 remaining go here, and 0 left. Right. So what is the accuracy of the machine? What is the accuracy? Huh? What is the accuracy?
90%.
Okay, so it's how much? 45 upon 50. 90%, right? Now, I was a bit smart. I knew that how many people will have COVID, 1 or 2. Let me make a false system, a fake system. For every person, it will say they don't have COVID. Now, draw the confusion matrix. My machine, for everybody, it says they don't have COVID. It's a fake machine, does not do anything, just gives an output, you don't have COVID. What is the accuracy? So draw the confusion matrix first. The same labels. Yes? No, the confusion matrix. 0, 1, 0, 49, right? Because for everything machine is saying 0 only, or the negative only. Oh, this is negative. And only 1 is, 49 are correct, but 1 is wrong. So what is the accuracy? 1 upon 50. Which is a better model? Yeah, so my fake model wins the game. Right. I won the match because even if I made a fake model, but I still won the match. This means there is some problem with our matrix. Can we have better matrix? So the better matrix are precision and recall. So precision is defined as true positive upon true positive plus false positive. What is the precision for the top model? Let's say this is model A, this is model B. For model A, what is the precision? Yes? 1 by 6. And for the B model, precision is? Precision is not defined. Other metric is recall. It is defined as true positive upon true positive plus false negative. What is the recall of the A model? Recall. Recall is 1 by 1. Okay, 1. Recall of B model is 0. Now very clearly you can see which model is better. Which model is better? A model is better. And even if it out of 6 times if it says COVID is true, only 1 time it is correct, but it is able to capture all the people who have COVID using these statistics. So this is a better model. That's the utility of precision and recall. Now again you have 2 metrics and you want to make single metric, so you take the average of the 2. But don't take normal average, take harmonic mean. Why harmonic mean? The utility of harmonic mean is that harmonic mean is always less than both the entities. Like less than this and less than that also. Oh. Is it true? I don't know. It is? Yeah, it favors the lesser value. It may not be less than the lesser value. Less than the average, yes, that's true. But it may be more than the lesser value also. Yeah. So basically it favors the lower value. So it's called F1 measure or F measure. It is defined as harmonic mean of precision and recall. So which means 2PR upon P plus R. Right? That is the harmonic mean of precision and recall. Oh, sorry, 49. Yes, thank you. Okay, so these are some metrics, but of course, they are not exhaustive. Depending on your problem, you can define your metrics. Let's say you are making a metronome. Oh, what? Metronome, you're not using machine learning. Okay, when you make something with machine learning, you can define your metrics. These are the common ones for classification, but depending on our problem, you can define so many different kinds of metrics. Okay, then let's come to, so we discussed about if you have a model, if you know the W or if you know the M and C, then how do you evaluate your model? How do you kind of check? Okay, another thing which we just missed. If I give you 1 million points and you make a linear model, what is the computational complexity of that model, of evaluating 1 point? Or if I give you this unknown, the world gives you one unknown point and asks your model what will be your computational complexity to tell the answer? O1. It's constant, right? Let's say your model has got this equation, just 2 multiplications or just 1 multiplication and 2 additions. It's always constant, no matter what is the size of your data. So O1. Right. So that's the utility of Yeah, what's your name? Yeah, who Aditya suggested this. Oh, sorry, Vineet suggested this. So Vineet's model, that's the utility. Utility of any? Pre-trained? If you don't use the training data when you get test data. Yeah, I'm saying only for testing or only for evaluating complexity is 1. Of course, in the background you have training which will have its own complexity. But the runtime or when you are deploying it, at deployment time, complexity is constant. But here with the nearest neighbor method, the runtime complexity is very high. You don't have any pre-processing complexity, but runtime complexity is very high. Yes. Okay. What's the time now? We have 15 more minutes. Let's quickly discuss about optimization. So now we want to train the model. We want to train that W vector. So how will you do that? How do you optimize? So first thing is you have to define a function which you want to optimize. Let's say, I may say my function which I want to optimize is expected value of y minus fx. Where do you understand the meaning of these notations? How many of you do not understand the meaning of these notations? Different things. Okay. So this E is called the expected value. Expected value means, you have studied probability theory. It is expected value of anything is anything into P of that random variable, probability of random variable, integrate over the entire space, the space of that random variable. So that is the expected value. Or an approximation of expected value is average. If you have given samples from that PDF, let's say this data is a PDF, right, the real data, and x comma y are few samples from that data, then to approximate the expectation, you can simply take the average. So which means this will become equal to y minus fx, let's say yi minus fxi whole square, sum over all I equal to 1 to capital N, let's say. Right? So expected value becomes the average. So expected value of y minus fx whole square. What is y? Y is the ground truth. What is fx? Fx is the model output. And L is the function which you want to minimize. It's called the loss function. And it's the function of the parameters, and you want to minimize it with respect to the parameters. So that finally your parameters W will be equal to argmin L. L is a function of W. You can write it as it's a function of W given the data. All right. So in our linear case, fx will be a linear line, wx, w transpose x plus w naught. Right. Okay, let's take the linear case first. For linear model, look at this average thing. Fx is a linear equation, and L is a function of W, and L is what kind of function? Quadratic function in W, right? Quadratic in W. And can you find the minimum of L with respect to W if L is quadratic in W? How? Slope will be equal to 0 there, right? You know this is the thing. At minimum, it has single minima. So at that minimum, you will have slope equal to 0. Just say derivative of L with respect to W is equal to 0. That's a simple equation, linear equation kind of. And then you solve for that equation, and that's your answer. Right? Very easy to find the optimal W. But nonlinear models are more powerful than linear models, right? Who stops you from making fx more complicated than linear form? Linear form is good, analytically easy to work with, but not very powerful. What if I had a data like this. Let's say my roses are here. They were circles, huh? And my jasmines or my lotuses are like this. Can you fit one straight line to separate the two regions? We can't. We have to make some non-linear boundary, maybe like this, something like this. Some non-linear boundary is required. That's why non-linear models are more powerful. They can construct non-linear boundaries or separators. So for a non-linear boundary, my fx will become a non-linear function of w, which means L will not be quadratic anymore. L will have very complicated form. How will you find the minimum of L then? So we have to use iterative optimization. We'll use iterative methods. And a very popular iterative method is called as the gradient descent algorithm. The gradient descent algorithm is a very popular iterative method to find the minimum of L. So what is this method? It says you are sitting at a W. Okay, first let me tell you this thing pictorially. Pictorially it is, let's say this is L as a function of W and this is W. Let's say it's a linear, that means a single variable W. Let's say my L looks like this. It's a nonlinear function, but I want to reach the minimum. I want to reach here. This is my W star, or where I want to reach actually, right? So what this algorithm says, start with a random W. Maybe I will start from here. Then what will you do if you want to make it descend to the W star thing? You will look at the slope there, right? Whether slope is this way or that way. If I fall here or I fall there, slopes will be different. If my slope is positive, let's say here, then I should go in the negative direction. If my slope is negative, I should go in the positive direction. Means my W should increase. If my slope is positive, it should decrease. Right? So mathematically it will be W becomes previous value of W minus, okay, may not put it here, minus the slope. Right? If my slope is positive, decrease W. If my slope is negative, increase W. But now the thing is that how much to increase, how much to decrease? So I have to have some control on my step size. That step size is eta. Let's say I'm sitting here and I decrease it by 100 and I will be outside the graphs. Right? So I have to control my step size. That step size is controlled by eta. Generally we take eta to be small so that it may take small jumps and finally it will reach W star or reach close to W star. Because close to W star, my slope will be almost very small. My movements will be very small. So just stop there, somewhere close to W star. That's fine. All right. This is gradient descent algorithm. If you want to read more details, then I have recommended a book called PRML by Christopher Bishop. That's a good book. But if you want something quick, lecture videos are there on YouTube, on MLSP course. You can watch them, or feel free to find any other resources also. Okay, any questions up till now? Other things I will discuss in the next class. We have now about 6 minutes, 7 minutes left. Any questions do you have? No questions? Or if there are no questions, then I will discuss one more topic.
Like in starting, you told like if we that by the example of the district. In that example, how do we know the exactly starting point of the
How do you know the starting point?
Like you said, yes, we will know it by surely by causality and
Oh, I said as soon as the stick will touch the board, at that point the amplitude will start rising, right? Amplitude of your sound it will suddenly start rising. That point is the onset time.
how will we know exactly how will we measure it? If the sampling time duration is that large, that onset time is between those two samples, that we will not know exactly.
Yeah. Yes. So yeah. So your sampling time is the limit. Means you can't go subsampling time. So assuming that our sampling time is sufficiently large, you just pick that point. So our sampling rate is sufficiently large. I'm sorry. No questions?
Sir, in terms of an audio sequence just made using instruments, we can decompose it into a set of frequencies or like a length, like audios are given, for example, sinusoids are given frequencies with different delays played in the sequence, right?
Once again.
So basically, if we play some sort of a group of instruments together, no vocals for now, then we can decompose this mixture of audio into some fundamental frequencies or fundamental instrument patterns, right? Then can we, I mean, my question is there some sort of study which focuses on what kind of instrument pattern mixtures are the best, make up the best audio in terms of human attractiveness to the audience?
Okay. Good question. Good question. So his question is that if you have an ensemble of instruments playing or multiple instruments playing together, then is there some study to tell which instruments sound most attractive to humans?
I mean, in a theoretical sense, a song which is always a hit.
Yeah. How to find a hit song or how to predict a hit song? Let's say you are a music producer and you got some people have made some music recordings they give to you. They say, please invest money and make copies of this and sell it, and we are sure this will be a super hit music, you will make tons of money. So should you invest your money there in that song or not, right? So if you have an algorithm or a machine which can tell you this music is likely to be very hit, but this music is likely to be very flop, so you can choose where to invest your money, right? Good problem. So this, think about it. How would you go about solving this problem?
Let's discuss some.
Huh?
I have an approach. I'll discuss it with
You have an
you.
approach. Okay. So how there was a paper in 2013. I was in a conference, and there they presented this paper, how to predict a hit song. And so what they did is they took the song, they made a data set first of all. You remember this? You have to make the world has to give some data set for supervised learning. They did it in a supervised learning method, that you take some songs which are hit songs, take some songs which are flop songs, make a model, a black box kind of, this kind of a model, like nonlinear neural network kind of model, give it as an input, a song as an input to the model, and the model will predict whether it's a hit or a flop. And if it is trained on sufficient amount of data, which means hit songs and flop songs, then the model will be able to predict it for an unknown song also. That's a simple approach. It may work or may not work. It won't work. Yeah. It will have a lot of bias, yes. So for example, it may pick up only songs from A.R. Rahman, not from others. Or it may, so which means that now tomorrow if Sanjeet says, I want to become a musician, he approaches the producer will simply blindly run his algorithm and he will say, sorry Sanjeet, I can't invest in your music. And this is like cheating, right? Even if Sanjeet may be a top class musician, but just because the machine was trained on A.R. Rahman songs and it only says A.R. Rahman song is the hit song, every other song is a flop song, then this is called bias in machine learning. We'll study more about it, how models can become biased on some unknown factors. Right? Okay. So that's the danger of machine learning. The machine learning gives you some prediction, but should you trust it or not? I don't know. Especially for decision-making problems. Okay. Any other question? Any other question? Are you sure you are ready for the submission of assignment on Monday? If you have any questions, feel free to ask now. So, submission will be in class. So bring your printout or handwritten paper and submit. I think printout is better with all the write-up and the images, and present it in a way that I can understand it very quickly. If you present it in a very kind of convoluted way or very difficult to decode way, I'm not going to give marks. I have limited time. I will just look at your answer. If it appeals, it is passed. If it does not appeal, it is fail. And if it is badly written, not well presented, fail for sure. It may be best method, but not well presented, then I will not read it. All right? Okay. So bring your sheets in the class and submit here. Write your name on top and submit here. No online submissions, no, no later submissions. Everything in the class. All right? Any questions regarding the problem?
So we have to just submit for the metronome.
Both. Two sheets basically. Okay. Thank you then.